Next is partial change, or sometimes what we call marginal effects. So what is marginal effect? What is partial change? Well, marginal effects and partial change tell us how a dependent variable, or the outcome, in this case, is going to be predicted probability change when a specific covariate independent variable, explanatory variable change. In this case, with a very small amount, And for the predicted probabilities from multinomial logic models, the marginal effects, if we're talking about predicted probability as this response outcome, here we need to use the quotient rule to figure out. Recall that the formula for calculating predicted probability is a ratio. So the first general differentiation rule we're going to use is the quotient rule, and then everything else follows. So by careful derivation, we can figure out the partial change or the marginal effect of the predicted probability with respect to a single covariate. The partial change is equal to, first of all, is a probability. So it is a product of two things, two terms. First is probability y equal to m. How to figure that out? Well, we just plug in, beta for the formula, in the formula that we just talked about in our previous slide. And on the right is a bracket. And the bracket is a subtraction. So first is this term. This is term comes from the slope for the xk variable, okay? The variable of our interest. We want to figure out the partial change or marginal effect, okay? From the odds comparison equation of m versus, so lowercase m versus capital letter M, okay? Minus, okay, summation of several products, and each product comprises two terms. Okay, each product comprises two terms. First is again the slope for xk, the slope for the variable of our interest of the covariate we're trying to find out its partial change. But for the odds comparison of J, so a generic response over the reference category, capital letter M. So in this case, it's not y equal to lowercase m, but from j equal to 1 to m. So first is beta k, that is the slope for xk, the variable of our covariate of our interest, for the odds comparison of 1 versus m. Okay, that odds comparison equation multiplied by its corresponding predicted probability given x. So in the first case is y equal to 1. Okay, so that's one term. And for the second term is again this beta k for a different odds comparison. Okay, for different odds comparison. Okay, and in this case, it's going to be 2 over m, odds comparison. So a different beta k, okay, for the same covariate, and y equal to 2, until we hit, capital letter M over n, right? Y equal to m. Well, we sum across, we get a summation, and subtracted from this term, then multiply by the predicted probability. So a kind of, a convoluted computation here, but we don't have to worry about it because the computer or some user-written R package or functions can do the work. Okay, so here just give you a general sense how the partial change is computed. Since this equation combines all of the beta k, okay, that is slope for xk covariate for the odds comparison equation of j over capital letter M. The marginal effect of xk on M, okay, y equal to M here, need not have the same sign as the corresponding coefficient of beta k, this lowercase m over capital letter M, okay? Further, as xk changes, the sign of the marginal can change. For example, at one point, the marginal effect of education on having a laborer's job could be positive, while at another point, the marginal could be negative. Okay? In short, partial change of marginal effect tells us how a outcome response, in this case, predicted probability change when a specific covariate, okay, explanatory variable change, in this case is xk, and at specified location, okay, so it tells us basically the relationship effect of x on predicted probability at certain location, because this is a nonlinear model. As we change the location of xk or other covariates, then effect is going to change. Okay, so at every location, the effect is different. Okay, here I'm talking about, when I say effect, here I'm talking about as x change a little bit, and how much y going to change. So this is partial change. Next, let me talk about discrete change. Well, consider the change in the predicted probability when xk, again, a generic covariate, change from x of s, starting point for this covariate xk, to the ending value of x. And note that here, in this case, we're going to hold all other covariates except this generic variable xk to specify values. Once we change the values of locations of other covariates, all the values, actually, all the quantities of interest that we're looking at, actually going to be different. In this case, the discrete change is, right, so this is discrete change, difference, right, in the predicted probability is equal to, well, we begin with xk equal to ending values. Where this xk ends, we calculate the predicted probability given, well, the estimated maximum likelihood estimates of betas, right? Then we subtract another predicted probability computed using starting value of x for xk, right? We can compute two predicted probabilities and then take a difference, which can be interpreted as for a change in variable xk, this generic variable xk, from x starting value to x ending value. The predicted probability of outcome n changed by the delta amount, that is difference in the predicted probability. Holding, remember that, holding all other variables constant at specified values. So at specified values, okay? Not only constant, but at specified values. Once we change the values of other covariates, then that discrete change gonna change. Same gonna apply to partial change. Because the model is nonlinear, the discrete change depends on the amount of change in xk, the starting value of xk, that is xs, and the value of all other variables. Of course, the ending value of xk, that is x of e. Okay. And let me talk about discrete rates of change. Consider the change in the predicted probability when xk, again, changes from s of xs, subscript s to xe, that is x ending, okay? The discrete change is defined by this quantity, right? That is the amount of change in what? The response outcome, all right? Pretty probability with the amount of change in xk. That is, in this case, is x subscript e minus x subscript s, right? In the numerator, we have, of course, we have this difference, right, in pretty probability. And the denominator, we have delta xk, which can be interpreted as for a change in variable xk from x subscript s to, x subscript s to x subscript e, the discrete rates of change. So in this case, is rates of change. And the pretty probability of outcome n, so in this case, is for a generic response for y, okay, is this ratio. So note here, we're talking about rates. So on average in this range, it is on average in this range, okay, if you change, that's 1 unit, okay, in xk, what's going to be the amount of change in the pretty probability? Only within this range, okay? And this is an estimate of this averaged discrete change. So that's the reason why we call that quantity discrete rates of change. Holding all other variables constant at corresponding specified values. Again, different from odds ratio coefficients. We have to say for probabilities, okay? Or when we talk about marginal effects, we have to talk about corresponding specified values. Once these values, the specified values of covariates change, then partial change, marginal effects, and discrete change are going to change. Because the model is nonlinear, the discrete change depends on the amount of change in xk. Okay, the starting value of xk, and of course the ending value of xk, and the values of all other variables.